Good morning. We're starting chapter 30. We'll begin with a discussion of why it is that the orbital radii for the electron orbiting the hydrogen nucleus are quantized, meaning that only certain values are allowed. We say the orbital radii are quantized. I show a circular orbit around which the electron with a negative charge, negative E, is orbiting. At the center of that circle is the attracting a proton. Radius of the circle is r. Mass of the electron is m. The values of m and r and E are known. I won't state them here. For the record, I will say that for an electron to orbit the hydrogen nucleus in a circular path, you must be able to fit a whole number, an integer number of wavelengths around the path. Stated this way: n times lambda, where n is some integer like 1 or 2, 3, 4, is equal to the circumference. We'll later refer to n as a quantum index or quantum number. Let's rewrite lambda using the de Broglie wavelength equation, where lambda is h over p, where p is the momentum. So there's your n, and the parentheses is h over p, h over mv, still equaling 2 pi r. We're going to rearrange this equation and solve it for v. Bring the v over here, and the 2 pi r goes downstairs, and switch left and right, and I obtain v equals nh over 2m pi r. We'll use this very soon. Now we apply Newton's second law to the orbiting electron. The force causing the circular motion is the electric force, kqq over r squared, maybe you remember, where the q's are absolute values of the charges. The two charges are E and negative E. Their absolute values are E. So the force is ke times E, ke squared, over r squared, ke squared over r squared. The centripetal acceleration is the acceleration we have here. The centripetal acceleration is v squared over r. You may remember from a long ago course, Physics 23, Chapter 5. Well, maybe not. I multiplied both sides of this equation by r squared. R squared times this. One of the r's cancel, and you end up with an r outside upstairs. I leave the equation just as it is, except I'll replace the v that is squared here with this parentheses, which is this one back here. So take that, put it in the parentheses for v, and square it. Don't forget the r outside. Now I'll repeat this equation up here, except I'll square the parentheses. So you have the ke squared, no change, and m outside. The numerator squared, n squared, h squared. The denominator squared is 4, m squared, pi squared, r squared. Don't forget the r outside. Well, some cancellation occurs. You should be able to see. That m cancels one of those m's there, and that r cancels one of the r's there. So I repeat the left side. The parentheses unchanged in the numerator, but there's an m to the first power and nothing else except the 4 and the pi squared and the r. I'll take the r and multiply it over here and divide by ke squared. and you get n squared pi squared. Well, you can see 4m pi squared ke squared. I'm going to pull the n squared outside, put it there, there it is. And in anticipation that the value of r that we're going to calculate will depend upon the value of the quantum index n, I'll subscript that r variable with the letter n. Your n squared came outside, leaving behind this parentheses without the n squared inside. All the values shown in the parentheses are knowable. You can find them in the notes. Planck's constant, the mass of the electron, the value of pi, of course, the value of the electric force constant, and the charge E. When you put in those values, the standard units, this is what you get. I'll rewrite it in terms of 10 to the power of negative 10 because 1 times 10 to the power of negative 10 is 1 angstrom. And so we have final result, r sub n, the nth quantum radius, is n squared times that parentheses in angstroms, where n can be 1, 2, or 3.